I suppose I can wait another 5 milliseconds. So you can set up a time and say, okay, wake me up in 5 milliseconds. So during that 5 milliseconds, all the other threads, all the other queues will basically be able to run. But as soon as the 5 milliseconds is up, guess what? This will take control away from anyone else who is running in the system at that time. So that's what I mean by time-based scheduling. You're basically saying that I want to resume execution in X amount of ticks or milliseconds. And then we have time slicing, which is related to the preemption. Okay, you're basically saying every so often the kernel will come in and say, okay, I'm going to take control away from whoever has control for the past 5, 10 milliseconds or whatnot. And then we have inter-thread synchronization. In other words, how do you make a thread wait for some resources that is managed by another thread? Sometimes they have some interaction. And the way to do it is to use semaphores in this case. And I don't want to get really a whole lot into semaphores. The semaphores are related to mutex, which is a feature supported by pthreads. So we'll get to that. We don't have enough time to cover that today. But I do want to get to the part where you can see some actual code. Okay, so these are files that are, supplied by the real-time kernel. Everything is done by done in assembly in this case. So I want to go up and then go down to section. I want to go to the API, the application program interface part. A struct thread is used to represent a single thread. It's a small data structure to keep track of the priority, the semaphores it's waiting for, that sort of thing. A queue is basically a ring here. So a thread is a bubble. A queue is basically a linked list that is a ring here. And then the last one is all the queues. So everything together, this entire thing, the entire stack of stuff is an array. It's implemented by an array in this case. Okay. And then we have, other data structures supported. This is not important. And this is starting to become important. RTK initialize is the first call to this particular real-time kernel so that the real-time kernel itself gets initialized. In other words, in this particular architecture, the real-time kernel is not a mandatory feature. Okay, if you do not call RTK initialize, there's no operating system, no kernel whatsoever that is running at that time. When we call RTK initialize, it will first initialize the kernel itself, and then it will also automatically associate the current function using the current stack to become the first thread. And that first thread is represented by the thread structure that is pointed to by T. So this makes the very first thread of the entire system while you initialize the real-time kernel. Because before this call, there's no representation or there's no illusion of threads whatsoever. This is the first call to do that. So it supports two parameters. One is to say, okay, what data structure should I use to represent this particular thread? And the second thing is, where should I put this thread here? The default thread, should I put it as the highest priority one, the lower one, or the lowest one? So you get to choose the priority of the very first thread of the entire system. And we have 1 more minute. This one is for you to create a new thread. So you have one thread running from the RTK initialize call. After that, you can create additional threads, which is basically doing the same thing as a fork, except it is not dealing with processes, it's dealing with threads. This is a data structure to represent the new thread, and this is the priority level of the new thread. This is the stack pointer. In other words, you have to specifically say this thread is going to use this memory space here as its stack. Okay? And that gets a little bit tricky because you have to guesstimate how much stack space is needed by a specific thread. And in this case, there's really not a whole lot of profiling utility program to help you determine that. So a lot of that is trial and error. This is also important. this parameter start is the entry point of the function that will basically be the root of the entire thread. So the execution of this function becomes the starting point of that particular thread, and it also supports, that function supports a void pointer, so it can pass parameters just like pthread does. Pthread allows you to pass parameters to the threads that you're starting. And then the last part here is param, and param is basically passed to this parameter of the function that you will use as the entry point of the entire thread. And pthread operates pretty much the same way, minus the queue part, but it has all the essential parts, just like this when you add a new thread. It is just amazing to me, after reading this and also the pthread documentation, that the two real-time kernels or the two kernels have so much in common, because I did not know anything about pthreads when I wrote this, because I do not have the resources like Linux does when I deal with the architecture of this size. That really tells you about the efficiency of a thread, because if I can do it with an 8-bit processor with 4 kilobytes of RAM and maybe 128 kilobytes of flash space for the program, the footprint of this kernel is 2.5 kilobytes. 2,500 bytes is the footprint of the code size. What?
That's more than half your available space, isn't it?
No, this is the code space. I have 128 kilobytes for code, and of which 2.5 kilobytes will be used for the real-time kernel.
Oh, so it's like 4 kilobytes.
It has 4 kilobytes of RAM space, but how much RAM this will consume depends on how many threads you want to have, and what is the stack space for each thread, and so on. So that part is less predictable, because it is not based on the code itself, it's based on how you use the real-time kernel. So it's a very small footprint. If I can do it with an 8-bit processor, you can do it with a 32 or 64-bit processor. Let's make that the final project.
Real-time kernel?
How about integrated? Well, does it work? Does it work? Yes. No. Yes. No.
You should try and find an embedded board with plenty of GPIO pins that runs the Intel Atom processor. Once you get on that, you can have your micro math doing anything you want.